Right, question 2 is connected particle question. We have the diagram as shown there. It's a light inextensible string around a smooth pulley. So as with question 1, the first thing I'm going to do is draw my own diagram and put a bit more onto it. And I've got A is here. And it's got a mass of M. Light inextensible string down here with a smooth pulley. And then I've got B. And that, I think, is everything that's shown on the initial diagram. So let's put on some more detail here. Forces, I've got mg at A working downwards. I've got a reaction, got 2mg as a weight down at B. I've got a tension at B, and it's light and inextensible. The pulley is smooth, so that tension is the same with there. But we've also been told that A is sitting on a rough surface, and so friction, which is going to oppose any motion, pointing in that direction. So what have we got? Part A. Need to find the tension of the string immediately after the particles begin to move. So I'm going to consider at B, and I'm going to say downwards is positive. So what have I got? I've got F equals ma. I've got 2mg minus tension equals the mass, which is 2m, and times the acceleration. Now the acceleration was actually given to us, and it was acting that way, 4/9g. So that equals mass times acceleration, 4/9g. So that's my equation there. Tension rearranging is 2mg minus 8/9mg. And that becomes tension equals 10/9mg. Okay, for part B, we've got to show that mu equals 2/3. So we're going to be looking at A for this. So for part B, let's have a look at A. If I resolve vertically to start with, I've got RA minus mg equals 0 because it's in equilibrium vertically. So the reaction at A equals mg. And so friction equals mu r. And so friction equals mu mg. Okay, I'm going to resolve horizontally now, and that way is going to be positive. So looking at my diagram here, I've got T minus friction, so all the forces F equals ma going to the right as positive. T minus friction equals ma. Now we know, let's put in some numbers in here. I've got 10/9 mg minus mu mg equals mass, which is m, and times by a, which is 4/9g. Cancel out all the mg's there, and I'm left with 10/9 minus mu equals 4/9, which means mu equals 10/9 minus 4/9, which equals 6/9, which equals 2/3, which is what we're supposed to show. Okay, question 2, part C. Basically, it's telling us that B has fallen a distance h, and it hits the ground and stops. Particle A is then a distance 1/3 h from P, and we want to find out at what speed A is doing as it reaches P. So let's just put that on a diagram. So I've got the ground there. B is going to fall a distance h, and so A is going to move a distance h as well, because it's an inextensible string. And again, it tells us that particle A is a distance 1/3 h from P, so that is 1/3 h. And so basically A is going to be accelerated up to that point, because B is dragging it along. B hits the ground, so the acceleration then stops. Now we know the acceleration from the earlier part of the question, which is 4/9g. So A is accelerated up to this point here, at which point the acceleration stops, and we're going to have a look at how it acts after. We'll have to deal with this question in 2 parts. The first bit being as B is falling down. So let's consider at A. So this is at A during the acceleration. We know that it's starting from stationary, so U equals 0. We know from our diagram here that S is that distance, so S equals h. We know that acceleration is 4/9g. And we want to find the speed, we want to find its speed as it reaches P, so I'm guessing we're going to have to find the speed up to the point at which B hits the ground. So V is what we're trying to find. So let's have a look. I think the Suvat equation we're going to use here is V squared equals U squared plus 2AS, and I'm going to take that way as positive, so I need to define that. V squared equals 0 plus 2 times A, which is 4/9g, times by distance, which is h. And so V squared equals 8/9gh. Okay, that's V squared. If I find V, it's going to be a square root, which is a bit nasty, so I think at the moment I'll just leave that as V squared. And let's now have a look at the next bit. So after B has stopped, and we know at that point that tension equals 0. So I'm just going to need to consider A. mg, which we've got from the earlier part. There's no T, but I still have a friction. And friction we know from the earlier bit equals 2/3. That's mu times the reaction, which is mg, so 2/3 mg. Okay, so we're looking, so once the tension has stopped, the particle is going to start to slow down. We need to find out what that acceleration is, and we're going to use F equals ma, and I'm going to say that way is positive. So what have I got? I've got minus 2/3 mg, that's the only horizontal force acting on it, equals ma. And so A equals minus 2/3 g. It's negative, so that tells you the acceleration is acting in that direction. Right, so we're going to go back. We're going to use V squared equals U squared plus 2AS. And I'm going to use it that way as positive. Now just being careful here, my v squared, which is my initial speed, my u squared, v squared is what I'm trying to find, u squared is v squared from the first part. V squared is what I'm trying to find out, so u squared equals 8 over 9 gh. A is minus 2 over 3 g. S we know is 1/3 h. And so I'm going to use v squared, which is what I want to find, equals u squared plus 2as. V squared equals 8 over 9 gh minus 2 times this is negative because the acceleration is negative. 2 over 3 g times by 1 over 3 h. V squared equals 8 over 9, whoops, gone off the screen, 8 over 9 gh minus 4 over 9 gh. V squared equals 4 over 9 gh, which means that V equals 2 over 3 root gh, which is what we're trying to find. Last part of the question asks, state how the information, you've used the information that the string is light. Basically, if we go back to the original diagram here, there is no mass to that string. If there was, as that descended and more mass came around to this side of the pulley, you can accelerate, again, the tension wouldn't remain constant, tension would actually increase. So the main thing we're doing there is we're using that, say the string is light, just keeps tension as being constant.